one. Hello, everybody. Welcome to Chem 1211 with your host, me, Dr. White. And now I'll be going through Quiz 5 and Quiz 6 review. Remember that I will be giving quiz number 5 and 6 tomorrow, 7/24, 24 at 8 a.m. or earlier. I will email you the password for quiz 5 and also the password for quiz 6. You'll have until Friday, 7/26/24, 8 p.m. to upload quiz 5 to the assignment area quiz 5 and quiz 6 to the assignment area of quiz 6 in Blackboard. Keep them separate. Upload them to the separate ones. Quiz 5 has 5 pages, 9 problems, some multiple part questions, no multiple choice. It's worth 50 points. It covers chapter 15, which is chemical equilibrium, including the collision theory of reactions, rates of reactions, chemical equilibrium, and I'm going to use my Chicago French accent, the Chatelair's principle, which is not how you pronounce it if you know how to speak French, which Dr. White doesn't. All right, quiz 6 have 6 pages and 10 problems, including some multiple part questions, no multiple choice. It's worth 55 points, so that's five bonus points. And it covers chapter 14, acids and bases. You should know what is a Bronsted-Lowry acid? What's a Bronsted-Lowry base? You should know what are the chemical formulas of key acids and bases. In other words, identify things as acid or base. You should understand how to identify an equilibrium, an acid-base equilibrium. What's the acid? What's the base? What's the conjugate acid? What's the conjugate base? You should be familiar with the water dissociation reaction, which gives you the ionization constant of water. And acidic solutions, basic solutions, neutral solutions, should know how to identify that. You should be familiar with pH, the pH scale, which I gave and I'll cover today, and pH determination calculations, also what a buffer solution is and how the pH changes, and finally a titration. And I'll by Monday post the scores for quiz 5 and 6. And hopefully by Monday, things got real busy in my life. I apologize last day or two. I'll have all labs that you've submitted graded. I'm shooting for Saturday on that. All right, let's get going. Let's do quiz number 5 review. And the first thing I talked about was the collision theory. And you should know the important parts of the collision theory. In order for a chemical reaction to occur, such as A plus B makes C, A plus B makes C, first of all, A and B, the molecules have to collide for a reaction to occur. Now, when the molecules collide, they just can't go dink, they got to go boom. They got to, I don't know about boom, but they've got to have enough energy, and that's called the activation energy for a chemical reaction to occur. And for a lot of reactions, molecules have to be in the right orientation. Like when you put a key into lock, if it's upside down, it won't go in. Well, same thing when molecules come together to react, they have enough energy, but they have to be aligned properly. Now, we have something called the reaction rate. That's the rate at which products are made or reactants are consumed. Consumed is another way of saying used up. or reacted. Now, what are factors that influence reaction rate? Well, the physical nature of the reactants, are they liquids, solids, or gases? How much of the reactants you have, and this is very important. Hint, whenever I write something in red, it's very important. There's a rule of thumb. Oh, it's on this thumb today. And that was lame. But anyways, and you should know that the reaction rate, the rate of a chemical reaction doubles for every 10 degrees increase in the reaction temperature. So the rate of a chemical reaction doubles every 10 degrees increase in the reaction temperature. Also, you should know what is a catalyst and how does it work. How does a catalyst work? A catalyst works by lowering the activation energy to increase the reaction rate. By the way, a lot of your enzymes, I think almost all of them, are catalysts. Now, next I talked about energy diagrams. An exothermic reaction, you should know that's one that gives off heat. And an endothermic reaction, that's one you have to put into heat to go. So let's look at the energy diagrams for that. And this is an exothermic reaction. And how do I know that? Because the heat is on the product side, on the side of the head of the arrow. Now, how do you do that graph? How do you do let's go back and I'll show you the wording, the energy diagram for an exothermic reaction. We have an X and Y axis. On the X-axis, we have time. On the Y-axis, we have energy. Now, there's something called the conservation of energy, and you have the same amount of energy at the base of the arrow as at the head of the arrow. So let's artificially say the amount of energy is for A and B is this. Now, some of the energy when it goes to C is lost as heat. So because of that, C will have always the products or products less energy than A and B in an exothermic reaction. Now, how do you get from A and B to C? You go up the hill and over the hill and down the hill to grandmother Noah. And the next thing you should know on this diagram, the energy diagram, is how to show the activation energy. And the activation energy, called E sub act, is the amount you have to go from where A and B starts to the top of the hill. And that's an exothermic reaction. Remember, the amount of energy on both sides, conservation of energy in our chemical reaction is always the same. And because A and B had a certain amount, but you lost on this side some heat, it went away, C has less energy. Now, this is an endothermic reaction. And how do we know that? Because you have to add heat on the side of the reactants, D and E, at the base of the arrow. Now, once again, let me redraw my lines here. Give me a little more room to work with. And then the x-axis, you have time, and the y-axis, you have energy. Now, if we look at this reaction right here, we're adding heat. Remember, the energy on both sides is the same. So if we have to add heat, let's say D and E has this much total energy. Because we're adding heat, heat is a form of energy, F and G will have more energy, higher. And this is relative on these. So there it is. How do you go from D and E to F and G? Well, you go up the hill and over the hill, not to grandmother's house, but to F and G. And what's the activation energy for this reaction? The distance of where you start to the top of the hill. And that's the activation energy. That's how big much the collisions have to be. And that's how you do the two energy diagrams. For exothermic, since you're losing heat, the product will be lower than the starting material. For endothermic, because you're adding heat, the products will have more energy, higher than the starting materials. Now, next I talked about a chemical equilibrium. And that's two reactions that happen at the same time in opposite directions. And we show that by these double arrows. That means A plus B makes C and D, and C and D goes backward to make A and B. Now, you should know that at equilibrium, the forward and reverse rates of the reaction are the same. You should know that. So here we have an equilibrium, and there's a number that is very useful. That's called the equilibrium constant, K sub EQ. And the equilibrium constant for this general reaction is when we have something in brackets, that means concentration, moles per liter. So you have moles per liter of C to the power Y, which comes from the coefficient. When there's no number there, Y would be 1. Times, not plus. A mistake students do, they see this plus and they put this like this. And that's wrong. Really wrong, and I mark it wrong. It's a multiplication. So you have the concentration of C to the power of Y times the concentration of the other product to the power of Z. And that's divided by the concentrations to the various powers of the reactants. In this case, A to the power of W, you get that from this coefficient, and times, not plus, times B to the power of X. And that's how you get the equilibrium constant. And at a certain temperature, for any equilibrium, which has the forward and the reverse rates the same, that number is always the same, which is why it's called a constant. Now, certain things you should know about the equilibrium constant and the completeness, which side to products or reactants do you get? the larger K equilibrium is, the more products made. Let's take a look at that. Not me. Let's look at the whiteboard. Oops, I did script or cursive. So if the equilibrium constant K EQ is larger than 1, like much larger, the amount of products, the product concentration, is always going to be greater than the reactants. If the equilibrium constant is less than the reactants, now it won't go that far to the right. The reactants concentration, amount of reactants, will be greater than the product or products concentration. Time for Dr. White to be subtle. Is that subtle hint? Know this. Now, the next thing I talked about is Le Chatelier's principle with equilibrium. And the principle states, Le Chatelier's principle is a great French chemist, an equilibrium shifts to the side to reduce the stress to put on the equilibrium. And you should know concentration effects and temperature effects for exothermic and endothermic reactions. What does that mean? Well, let's take a look. Now, hopefully you've gone through the problem set for this chapter. That's not what I want. That's what I want. And let me make this a little bigger. All right, this is problem 8 from chapter 15, practice problems. Now you're given an equilibrium right here. What happens, and let's just do oxygen concentration, bracket means oxygen concentration, if you add more water. Now, at equilibrium, there's a certain amount of Cl2, certain amount of water, certain amount of HCl, and a certain amount of O2. So if you add more water at equilibrium, there was a certain amount. Now there's too much. Oh no, there's too much. Now, how do you get rid of that stress to bring it down? Water has to be consumed. One is to drop the level. Think about it. If you have 2 cookies and eat one, consume one, how many cookies do you have? Less, 1. That's how you drop down the number of cookies you have, by eating or consuming it. Well, same thing. To get the lower concentration of water, because we added more and made it too high, the equilibrium will shift this way and make more this and this. And that's why this increases, and that's why that decreases. Now, let's look at an equilibrium. In this case, this is an exothermic reaction. How do I know that? The heat's on the right. Now, C6H6 is benzene. If you take benzene and add hydrogen gas, H2, and you need a catalyst, but I didn't put it down here, you'll make C6H12 called cyclohexane and heat, a lot of it. So I'm asking what happens to the concentrations of benzene, C6H6, and C6H12 if you put it in an ice bath. What happens? Well, note, ice bath removes heat. And later on, boiling water, if you put it in there, adds heat. So when we put it into the ice bath at equilibrium, there's a certain amount of heat. Well, the ice bath removes the heat and it wants to be back here. So it's, oh, I need more heat. So how can it make more heat? By having C6H, the hydrogens, H2, react to make more of this and more heat. Well, if you're making more C6H12, the amount increases. Now on this side, that's reacting with the hydrogen to make more heat. And C6H6 is consumed. It's like eating 2 cookies, eat one, you only have one. Dr. White has cookies on the brain today. But anyways, that means if the C6H6 reacts, it's consumed and there's less. And that's why its concentration decreases. Now, just the opposite happens when you put it in a beaker of boiling water. Boiling water adds heat. So at equilibrium, there's a certain amount of heat. Now, putting it into boiling water, you have too much heat. And it says, oh no, you didn't know equilibrium can talk. But anyways, I've got too much heat. I'm under stress. I got to get rid of this excess heat. How can it get rid of the excess heat? Well, how do you get heat to be consumed? The equilibrium shifts that way. The heat reacts with C6H12 to make more C6H6 and hydrogen. This way it's being consumed, there's less. So if you're going to make more C6H6, it increases. You got more, the amount increases. The C6H12, you've consumed some, like the cookies, so you have less, and the concentration decreases. And that's Le Chatelier's principle. Oh, excuse me. I think your blood operates that way. And I forgot either your kidneys or your liver and also your lungs, I think, operate Le Chatelier's principle. Amazing, isn't it? Chemistry going on in your body. It does. All right, that's quiz number 5. Give me a second while I open some stuff up. Hold on, I'm looking for. Huh, I'll have to go online. Hang in there. Huh, I wonder why I can't find it. I'll have to post it later on today. Oh, I know why. I changed order. Sorry about that, everybody. All right, I found what I was looking for. All right, let's look at quiz 6 review. And don't forget, quiz 5 and quiz 6 review are in Blackboard. And let me show you where to find it. If you go course information, you'll see practice problems, lecture. The review is in lecture, and obviously the practice problem answers are in practice problem answers. All right, let's start out. I started talking about acids and bases. One of the most difficult things that happened early in the 1900s was how to really define what's an acid and what's a base. And this had to be both in water and not in water, non-aqueous chemical reactions. Or, and two chemists came up with the same theory, and it's named after both of them, and that's the Bronsted-Lowry acid-base theory. And you should know, what is a Bronsted-Lowry acid? Any substance that can donate a proton, which is H plus, to another substance. In other words, a Bronsted-Lowry acid is a proton donor. Here, take my proton. I'm a Bronsted-Lowry acid. Now, a Bronsted-Lowry base is any substance that can accept a proton H plus from another substance. Another way of saying that is a Bronsted-Lowry base is a proton acceptor. I accept it. Now, you should know not the names, but the structures. HCl, hydrochloric acid, H2SO4, sulfuric acid, HNO3, nitric acid. These are all very strong bases. And one of the miracles of life to Dr. White is we all have cells in our stomach that make hydrochloric acid, HCl. That helps break down the food. All right, now bases you should know: NaOH, sodium hydroxide, KOH, potassium hydroxide, NH3 ammonia. I don't have it here, but I should write it down. This is sodium bicarbonate, other known as baking powder. And you should know that also is a base and the structure. Now, it turns out water is in equilibrium with itself, but the equilibrium is mainly to one side. And that's why you see the bottom arrow much bigger than the tiny little top arrow. Water dissociates with itself to give H3O plus, the hydronium ion, and OH minus, the hydroxide. Now, this is an equilibrium, but because water is always in such a great amount, they took that out of the equilibrium constant and came up with something KW, named after me. I wish it was in place long before I was born, but sounds nice. And that's the ionization constant for water. And you should know at room temperature, which is what we'll do in this class, the concentration of the hydronium ion H3O plus times the concentration of hydroxide OH minus is 1.0 times 10 to the minus 14. Now I'll give you that in important information, quiz number 6. Now, when we talk about acids, bases, and neutral solutions, most of the time we're talking about something in water. Not always, but most of the time in your life, it will be. And there are different terms you should know. Acidic solution, that's a solution where the hydronium ion concentration is greater than the hydroxide ion concentration. And you should know what is an acidic solution. H3O plus is greater than OH minus. Now, basic solution is the opposite of that. The hydroxide OH minus concentration is less, oops, got that wrong, is greater than the hydronium ion concentration. And that's a basic solution. Now, sometimes called alkaline, like in your alkaline batteries. Batteries used to be acidic. And then I forgot how many decades ago, they found a way to use base, which are better batteries. The battery in your car is acidic, but the batteries in your flashlight or other places like are alkaline when they say alkaline batteries. Now, a neutral solution is when the hydronium ion concentration is equal to the hydroxide ion concentration. Let's go through that again. Acidic solution, hydronium H3O plus concentration, that's why I have it in brackets, is greater than hydroxide. Basic solution, hydroxide concentration OH minus greater than hydronium ion concentration H3O plus. And finally, neutral, they're both equal to each other. Now, this is pretty hard when you're playing with concentration numbers. And good news, somebody came up with an idea called the pH constant. And there's a pH scale. And the pH scale is a small number that used to specify if a molar hydronium ion concentration, what is it in a aqueous solution? And you calculate that by pH equal minus the logarithm of the hydronium ion concentration. Now, my gift to you, don't tell anybody I'm being nice, is if the hydronium ion concentration, H3O plus, is 1.0 times 10 to the minus X, then the pH is X. Now, this is probably the most important thing I'll teach you this semester for your own personal life. And this is the pH scale. It goes from 0 to 14. At pH 7, you're at neutral solution. Anything above 7 is a basic solution. Anything below 7 is an acidic solution. If you have a neutral solution and you add an acid, the pH goes down. If you have a neutral solution, you add a base, the pH increases, it goes up. And you should know that. Hold on, I better get subtle. See how subtle I can be? Hint, know this. It's probably the most important thing I'll teach you this semester for your own personal life. All right. And the lower the pH, the more acidic it is. The higher pH, the more basic it is. It's a logarithmic scale. So pH 2 to pH 3, that's a 10 times greater difference in the hydronium ion concentration because of the logarithmic scale. It's not just one little unit, it's a power of tens. Now, your stomach is acidic because there's an acid present. And that's why the pH is low. And also, which I don't teach in this class, it's how if you take my Chem 1212, you'll learn that that's what breaks down your carbohydrates, your proteins, and your fats and oils, and the things your body can use. Now I'm way beyond my knowledge of the human body. All right, here's something else important, a buffer solution. A buffer solution is a solution that resists major changes in pH when small amounts of acids or bases are added to it. So if I have a buffer solution, I put a small amount of acid, pH doesn't change. If I have a buffer solution, I put a small amount of base in there, weak base, guess what? The pH doesn't change. Now, before we move on, because I forgot to do it, let's look at two pH problems. And you should go through. All right, let's look at number 4. If a solution has hydronium ion concentration, H3O plus, 1.0 times 10 to the minus 3, what is the pH of that solution? And is it acidic, basic, or neutral? So we're trying to find pH. We're given this number for the hydronium ion concentration from important information quiz 6, pH minus the log of H3O plus. We put that number in. When this is 1.0 times 10 to the minus x, which it is, the pH is x, in this case 3. Now, is that acidic, neutral, or basic? And I have over here note, when the pH is below 7, it's acidic, so this is acidic. If it had been 7, it would be neutral, and if it was above 7, it would be basic. Now, let's look at number 7. If a solution has a hydroxide OH minus concentration of 10 to the minus 3, what is the pH of the solution, and is it acidic, basic, or neutral? So again, we're trying to find a pH, but wait, we're given OH minus equal 1.0 times 10 to the 3, and pH is minus the log of H3O plus. So you need 2 steps. In step 1, you solve for hydronium ion concentration. How? Hydronium ion concentration times hydroxide equals 1.0 times 10 to the minus 14. And let me show you something. And if you notice an important information, quiz 6, I give you this right here. So we want to get H3O plus alone on one side. Anything divided by itself becomes number 1. So to get rid of OH, I divide by OH concentration. But whatever I do to this side, I do to that, and I did. Well, this divided by this is 1 times H3O plus concentration. I get that. And this side is right here, 1.0 times 10 to the minus 14 divided by the OH concentration, OH minus. Well, we know that's 1.0 times 10 to the minus 3, so I'll put it in there. I didn't need that bracket there. Do the math, and you get 1.0 times 10 to the minus 11. Are we done? No. What we have is this concentration, H3O plus concentration. Brackets mean concentration. But we're being asked to do the pH. So now we have to do step 2. Where's that number 2? Fell off. But anyway, step 2, solve for pH. pH is minus the log of the hydronium ion concentration. That's an important information, quiz 6. I just figured out what H3O plus concentration is. I put it in. And whenever a number is 1.0 times 10 to the minus x, the pH is x. Well, minus x is 11, so the pH is 11. Now, is that acidic, basic, or neutral? If we come up here to the chart, you should know above 7, which 11 is, makes it basic. Oh, I got it right. Yay, Dr. White. Now, the final thing I'd like to talk about is titrations. And titration is a reaction where you neutralize an acid with a base or a base with an acid. Why is it called neutralization? Because you take it to pH 7, neutral. And at neutral pH, at neutralization, moles of acid equals moles of base. Now, for monoprotic, one that only has one proton to give up or accept, acid or base, I've got this wrong on here. No, I have it right. It's been a long day. I simplified. You have milliliters of acid equal molarity of times molarity of acid equal milliliters of base and molarity. You'll be given in a problem the milliliters of acid and base, and either the molarity of acid and asked to find the molarity of base, or you'll be given the molarity of base and asked to find the molarity of acid. And this is a very important calculation that chemists use every day in the United States many, many times. It's used heavily, what's called quality control, to make sure products you buy or the chemicals that are used in products you buy are what they should be. And Dr. White is one of the few PhD research chemists who also for a couple of years not only ran a research group, but I managed a quality control lab in a major chemical lab. Boy, that was a job. Because I was responsible that the quality of product being shipped from that plant was always correct. And we shipped about 2 to 4 million pounds of chemical a week. Yep, 2 to 4 million pounds of chemicals a week. And my chemists did a lot of titrations. In fact, I helped automate that to make their life easier. All right, let's look at a titration problem number 12. If you have to add 1.35 times 10 to the third milliliters of a 1.53 capital M NaOH solution, here's the key word, to neutralize 1.87 times 10 squared milliliters of an aqueous HCl solution, what is the molarity of the HCl solution? So we're trying to find the molarity of HCl, which is an acid. We're given the milliliters of the base and its molarity. We're given the milliliters of the acid. Now, from important information, quiz 6, Moles of acid equal moles of base. Therefore, milliliters of acid times molarity of acid equal milliliters of acid times molarity of acid. What are we trying to find? MHCl, the molarity of acid. So we want that alone on one side, and I made a mistake here. This line should be over here, not there. To get rid of the milliliters of acid, divide by it. Whenever I divide one side, I do the other. I did. So we now have, since milliliters of acid over milliliters of acid, ignore this line here, it should be over here. Boy, I made a mistake. Sorry. Well, I told you I don't walk on water unless it's frozen. Even then, I stay off. I make mistakes, and there's one. All right. Well, anyways, it's a minor one. Molarity of acid in this problem equals milliliters of base times molarity of base divided milliliters of acid. Well, the milliliters of base is 1.35 milliliters of the NaOH solution. The molarity is 1.53 molar. The milliliters of HCl is 1.87 times 10 squared. Milliliters cancel out, we're left with molarity. One side is base, the other acid, so we're getting the acid. We have three significant, three. Dr. White's in his three significant figures, and you get 11.0 molar HCl, which you could have also written 1.10 times 10 to the first. And that's how you do it. And with that, I'm done for today. Don't forget, this Wednesday, tomorrow, I'll be giving quiz 5 and 6 online. I'll send out the password tomorrow morning, and you have until Friday to get both of them uploaded to separate areas of the assignment area Blackboard. Ooh, excuse me. Also, Monday the 29th, Tuesday the 30th of July, Wednesday the 31st of July, next week, we will be having, you will have to take test number 2 and the final exam at the testing center only at Glen Ellen COD main campus. They're open from 9 to 5. You got to get there earlier if you want to take either of those. I'd highly recommend you go there one day, take my test 2 first, and then you'll take the ACS test final exam. The final exam is only worth 5% of your grade, but that could make a difference between an A and a B or B and C and so on. Now, the final exam is multiple choice. So bring a lead pencil, that's soft lead or a regular number 2 pencil, and bring a good eraser. Now, my hint to you, always use your good buddy, your good friend, unit analysis, both my test 2 and the final exam. Look at units. Now, since it's a multiple choice, the ACS final exam, if you're not sure, guess. In this test, you are not penalized for wrong answers, but hopefully you won't have to guess. With that, I'm done. I'm going to say, Gang gesund. Bye now. Bye.